thesis with the help of his supervisors, Carlos Escobar Ibanez and Susana Gabera Oban. And the thesis is about the search for the Higgs boson produced in association with the top quark using tau leptons with the Atlas experiment. Please, Pablo.
Well, welcome everybody, and thank you for being here. Well, today I will be defending my thesis, and most of the work that I carried during this time focuses on the search for a Higgs boson produced in association with a top quark. This thesis is structured as it follows. First, I will motivate the search. Then I will present our experimental setup, consisting of the Large Hadron Collider and the Atlas detector. The next step is to present our analysis and our results. And finally, I'll conclude wrapping up for what I have presented. Well, since the beginning of times, humankind has always pondered about the nature of matter. And the search in this field has led us to more and more complex models, culminating in the standard model of particle physics. These models describe the universe as built from the following fundamental particles. First, we have the fermions divided in quarks and leptons, the gauge bosons, which are the mediators of the interactions, and the Higgs bosons. The standard model also describes all interactions of nature except gravity, and these are the electromagnetic interaction mediated by photons, the weak interaction mediated by the Z and WB bosons, and the strong interaction mediated by muons. Finally, the mass of fundamental particles is provided through their interaction with the Higgs field. Now, the standard model is a very successful theory, but it still has tons of open questions. From the description of the dark matter and dark energy, the inclusion of gravity, understanding the nature of neutrinos, many other theoretical questions, or understanding the observed asymmetry between matter and antimatter in the universe. Okay, we will focus in these two particles, the top quark and the Higgs boson. The top quark was discovered at 1995 at the Boson, and it is the heaviest known elementary particle. Due to its large mass, it decays before hadronizing, which allows us to study it as a free quark. It decays almost exclusively to a double B boson and a B quark, so its decays are often classified by the way the double B decays, being mostly to quarks. On the other hand, we have the Higgs boson, the second most massive particle, discovered about 11 years ago at LHC. And it also has a very short lifetime, and its largest theoretical decays that to BB bar. But what is important to us is not only these individual particles, but their interplay. And of particular interest is the Yukawa coupling between the top quark and the Higgs boson, because this coupling is the only one on the order of magnitude of the unity. And we can measure it only via the associated production of a Higgs boson and top quarks. There are two ways of doing this. Either with a pair of top quarks, this is the TTH production, which is sensitive to the magnitude of the Yukawa coupling, and the other way is via the production of a single top quark, which is sensitive not only to the magnitude, but also to the sign of this coupling. And you can see here how the cross-section of the TTH process does not depend on the sign of the Yukawa coupling, but for the TTH production, it does depend on the sign. The reason is that the diagrams in which the Higgs is radiated from the top quark interfere with the diagrams in which the Higgs boson is produced from the double Bs. And the standard model predicts this interference to be a destructive interference. Nevertheless, in a scenario in which the Yukawa coupling has an opposite sign with that which is expected by the standard model, we will have a constructive interference, and hence the cross-section would be an order of magnitude larger than the expected by the standard model. Now, this has been already searched in the past, but there has been only one dedicated search for the TH process that was done by CMS using the early run 2 data. Us, in order to be as sensitive as possible, we will try to cover as many final states, and we classify these final states according to the number of line leptons and hadronically decaying taus in the final state. So On one side, you have the single lepton channel. In this channel, we explore the Higgs decay to BB. I remember that was the leading decay mode. For the multileptonic channels, we'll focus on the decays in a tau pair, a pair of double Bs, and a pair of sets. I will focus precisely on the channel with 2 light leptons and 1 hadronically decaying tau. In this channel, we are dominated by the Higgs decay to taus, although the different channels have different relative contributions. We will further subdivide this channel in 2 subchannels attending to the relative electrical charge of the light leptons. If the light leptons have the same electrical charge, we talk about the same sign channel. And if they have opposite electrical sign is the opposite sign. The reason to do this is because they have very different background contributions, so it's much better to separate the analysis. Let's explore our experimental setup now. And as we all know, what we do is basically accelerate particles close to the speed of light, collide them, and detect the products of this collision. Our machine to collide the particles is the Large Hadron Collider. This is the most powerful particle accelerator ever built, producing collisions up to 13.6 electron volts. It is located at CERN in Geneva, 100 meters underground, and it measures 27 kilometers. Here, the beams travel in opposite directions and collide at the points where our detectors are. These are ATLAS and CMS, our 2 general-purpose detectors, LHCb, which is focused on beamers on physics, and ALICE, that research the heavy ion physics, because LHC does not only collide protons, but it can also collide heavy ion nucleuses. In this thesis, I use the data of the run-2. This corresponds to that collected between the years 2015 and 2018. The 140 femtobars I use are the ones considered for good physics, but these are most of the events that were recorded by ATLAS. And at this time, these are most of the events that LHC delivers, so we have very good performance. And since protons are collided in bunches, we can have several interactions in each batch, each crosses. We refer to this as pileup, and in average, we have 33 interactions per batch crosses. Although in each year, we have a different number because the instantaneous luminosity conditions change. Now, our machine, ATLAS. ATLAS stands for a toroidal LHC apparatus. So this is the largest detector of CERN, and this is a cylindrical detector with forward-backward asymmetry covering almost the entire solid world. Its dimensions are 44 meters in length, 25 in diameter, and it weighs 7,000 tons. From the innermost to the outermost, its detectors are the tracker, the calorimeters, and the muon spectrometers. ATLAS also has a two-level trigger system that filters out the unimportant events, and then it distributes this data to different research institutes using the worldwide LHC computing grid. Let's explore our subdetectors. The first detector that we have is the inner detector, and it reconstructs the tracks of the charged particles. This subdetector is immersed in a 2 Tesla axial magnetic field, axial meaning that it goes along the direction of the beam pipe, and so that it bears the trajectory of the charged particles, allowing us to measure the momentum. Once a particle leaves the inner detectors, it forms the solenoid magnet, and the next detector, which are the calorimeters. We have 2 calorimeters, the electromagnetic calorimeter made of liquid argon and measuring the energy of electrons and photons, and the other calorimeter is the hadronic calorimeter made of alternating layers of steel and plastic scintillator, detecting the energy of hadrons. Now, the last layer of ATLAS corresponds to the muon spectrometer. Only muons and neutrinos make it this far, and when neutrinos leave the detector undetected, the muons track are reconstructed in the muon spectrometer. This detector is immersed in a 6 Tesla toroidal magnetic field, which is produced by the toroidal magnets that provide ATLAS with its characteristic shape. Now, ATLAS is a detector that provides excellent performance, but to have this performance, we need to have our detectors properly calibrated. And one type of calibration is the geometrical calibration. We refer to this type as alignment. And the alignment of the inner detector is basically concerned on determining the actual geometry of the tracking system and follow its eventual changes in time. So in this picture, you can see how by using the nominal geometry of Atlas, we are not able to reconstruct properly the track. But after the alignment, the track is correctly reconstructed, and it has a large impact. And these plots illustrate this very clearly. So we have a simulated distribution in Monte Carlo, and the unaligned detector is not able to reproduce this distribution. But when we align it, we can. So you see how misalignments can degrade significantly our analysis. The alignment of the detector is a track-based alignment. What it does is that it minimizes the residuals. And the residuals are the distance between the heat and the intersection point of the extrapolated track in the sensor plane. So we minimize this, and we do this minimization from the larger structure to the smaller modules. My contribution to the alignment is the development of the alignment web display, and it is an application intended for modeling, for monitoring the track-based alignment results obtained at the calibration loop. So it helps us to evaluate the alignment corrections. It provides plots related to the detector performance, and basically it allows us to spot any misalignment and take action as soon as possible. It also interconnects different databases, and basically this has been widely used by the Atlas collaboration in the tasks of alignment. Now that the theoretical motivation has been given and we know our experimental setup, let's move with the analysis. And the analysis is done in the following steps. So first of all, we simulate and collect our data. Then we estimate the rates of the reducible backgrounds. In parallel, we define a set of preselection requirements. On the events that pass these requirements, we reconstruct the events with the variables from the reconstruction. We define the regions, and finally, on these regions, we perform the data feed. So this is the structure of what is remaining from the doc. So first step, we collect the data, LHC, Atlas. With the output of Atlas, we reconstruct the objects, and we perform the analysis. At each of these steps, we are collecting different sources of uncertainty. For the simulations, it's the same. First, we simulate the hard scattering process, then the soft physics. Then we also simulate the interaction of each of our particles with our detector. The electrical output of Atlas is simulated as well. This is referred as digitization, and we reconstruct the objects as we did with the previous data. And then we perform the analysis. As in the previous case, at each step, we are accumulating and gathering sources of uncertainty. We have simulated all the processes that play a role in our analysis, starting from the signal, which is the THQ processes, and the most important backgrounds like PT bars, L+Js. I want to highlight that in this case, TWH is just a background in the thesis, not confused with the ongoing Atlas analysis in which TWH is considered a signal. Now, we define our preselection requirements. First, we demand that our events pass single lepton triggers. Then, we require a certain multiplicity on our final state objects. This multiplicity is the obvious one in terms of leptons, economically decaying taus. We also require to have between 2 and 6 jets, out of which 1 or 2 have to be detached. PT requirements are applied as well. So the leading electron needs 27 gigaelectron volts, the subleading 20, and the third lepton either 20 or 14, depending whether it is a light lepton or a tau. Eta requirements are applied as well, depending on the acceptance of the detectors. And this is what we have after passing the preselection requirements. And we can also see here the importance of subdividing our channel into subchannels. See how different is our sensitivity. In our opposite sign channel, we have only 0.002% of events, not even that. And at the same time, we have 0.89%. So this is much more sensitive. But not only the sensitivity, but the relative fraction of the backgrounds also change a lot. For the opposite sign, we're dominated by PT bar and Z+H. while for the same sign, we have the TTWB, TTH, TTZ, and TT bar backgrounds. Now, these backgrounds are categorized according to the sources, and these categories are irreducible and reducible. The reducible backgrounds are those which have the same final state objects that as our signal, and the reducible backgrounds are those arising from the misidentification of physical objects. In our case, we consider the misidentification of light leptons or the misidentification of hadronically decaying tau. In our case, this is the most important. And for you to have an idea of the impact that these misidentifications have on our analysis, I want to show you. Wait, it's not time for that slide. I was too fast. Okay, so we need to estimate our backgrounds. And what does it mean to estimate the backgrounds? Well, our Monte Carlo simulations do not properly describe the rates in which the reducible backgrounds are produced. So we need to use a data-driven method to derive scale factors that really scale our Monte Carlo. In our case, this method is the template fit method. And we use it on a region of the phase space orthogonal to the preselection. In this region, we require that our events fail the medium recurrent neural network for tau identification. What does this mean? That we will have a region of the phase space very rich in wrongly identified hadronically decaying tau. So in this region, we subdivide it in terms of PT beings, bit multiplicity, and progress. And we perform a fit to the data in these regions. We fit to the ejector width in the region with 1 bit and to a BDT output in the region with 2 bits. By doing this, we derive the scale factors that rescales our Monte Carlo. And the uncertainty of this method is assessed using the counting method. Now, to have an idea of the impact that this has on our analysis, let me show you these pie charts. So rapidly, the first column is what we reconstruct as leading lepton, what we reconstruct as subleading lepton, and what we reconstruct as an hadronically decaying tau. The first row corresponds to our entire Monte Carlo, and the second just to the signal. And I want you to look, in general, that the light leptons are most of the time properly identified. You see that the leading and subleading leptons will always reconstruct. This is the truth label, either a 2 electron or 2 muon, 2 electron or 2 muon. So the light leptons tend to be properly identified. But this is not the case with hadronically decaying tau. Less than 3% of times, what we reconstruct as an hadronically decaying tau is an actual hadronically decaying tau, while most of cases it's either a quark initiated jet or a gluon initiated jet. So this is our main source of background. Nevertheless, for the same sign, we don't have this problem, and the taus are reconstructed properly most of the times. Well, once we have identified our background rates, it's time to reconstruct our events. And reconstruct events means estimating the form momentum of the top quark and the Higgs boson. This is a very difficult task due to the presence of at least 4 neutrinos in the final state. The first step to perform the reconstruction is to assign the origin of the light leptons. What does this mean? When we consider that the hadronically decaying tau come from the Higgs, then one light lepton shall come from the Higgs and the other from the top. And when the leptons have opposite electrical charge, the lepton with the same charge at the hadronically decaying tau is the one from the top. And the lepton with the same sign with the opposite sign from the Higgs. So this is trivial in the case of the opposite sign. But for the same sign channel, we cannot do this. And we need a more sophisticated method. So in this context, I developed a MBA-based method to assign the origin of the light leptons. So the first step is to take the events that pass the preselection and set a label, because in order to train a machine learning method, we need a label. Once the label has been derived, we train the model, apply the score, use it to assign the origin, and with this origin, then we can build variables that will be very helpful when defining the regions. Let's see these steps more closely. Okay, to define the label, what I do is to compare the particle level information, in which we know the origin of the particles, with the reconstruction level information. The reconstruction level information is the information as it comes from the detector. So what we do is to draw delta R cones around our reconstructed lepton, the blue ones. We draw these delta R cones. And if within this cone we have a particle level lepton, we say that these two leptons are the same. So we have two like leptons, we require this match to happen for both leptons. And now, once this matching has been done, we know for each reconstructed lepton whether it came from the Higgs or from the top. Well, I define them in two categories with very, very imaginative names, type 1 and type 2. Type 1 refers to the events in which the leading lepton is the one from the top, and type 2 is the one in which leading leptons comes from the Higgs. Now that we have our label defined, we can then train our machine learning method. I decided to use the TMJ library to train this guy in BDT. And the first step is to optimize the variables. In this case, I choose the variables that provide the separation between the two types of events. And I also pay attention to not duplicate variables with respect to the BDT that I will train for region definition. Now I have to select a negative weight strategy. I decided then to drop the negative weights. And if someone doesn't know, this is because BDTs cannot deal properly with negative weights in the training. So we have either to remove them or use positive weights. Well, we see that by removing the negatively weighted events, the distributions have the same shape as you see in the positive ones. And also the relative fraction of negative events is the same for both types. Therefore, we are not biasing our model by removing the negative weights. Now we have to optimize the parameters. I did this with a simple bit search. And the training is done using the key-folding method. And this is very easy, but since I will use it tons of times, I will just explain in 1 minute. The key-folding method consists on taking our data set and dividing it k times. In our case, k will be 5. So we divide our data set in 5 sub-data sets, and we will train 5 BDTs. And for each BDT, we will use all the splits except one for the training, and this one will be the one used for test. And for each model, the test split will be a different test. In the end, we will inject the BDT score to each event that was used when this event was on the test sample. And by doing this, we make sure that the model is not biased because the BDT that was injected has never seen the true label of the events. The result of this is 5 models that we combine into a single one, and then we set a threshold. And we have optimized this, but really whatever that lies in here is just uncertainty. So we put it at 0, and whatever is on this side, it's type 2, and whatever is in here is type 1. So leading lepton from top, leading lepton from Higgs. And this method has an accuracy of 95%. Now that we have our events more or less reconstructed, we can define the regions. Defining regions is just setting regions on the phase space that are enriched either in signal or in a particular background that we want to control. And to do this, I'm using BDTs based on the XGBoost library. Again, I use the k-folding method. The negative weight strategy is different for each BDT, and the variables are optimized using an iterative algorithm. The hyperparameters of the training are also optimized using the genetic algorithm, an algorithm inspired by the concept of natural selection. Actually, was quite fun developing this. Well, I trained 3 BDTs, one that separates THQ from all the other processes in the opposite sign. One that separates the 2 main backgrounds. I call this BDT or TT bar, and it separates TT bar and Z+Js. And the BDT that separates signal from background in the same sign. These are our 3 binary BDTs. And these are the variables I use for these BDTs. Many more were tested, but with our iterative algorithm, we were able to decide how many variables and which we wanted to input in each model. A good thing of BDTs is that they have rankings of importance, which allows for interpretability. So, for instance, in the case of BDT of TT bar, the high free run variable is the mass, the variable mass of the two leptons. This has a clear interpretation. This variable is speaking on the set boson mass. So what this VT does is taking these events and assigning them to as they were set plus jets. So it easily separates set plus jets and CT bar by looking at this variable. So this is a nice thing of the VDTs. And this is how our VDTs look. I see the separation plots, I like them more. And you see how for the VDT that separates the signal from background, the backgrounds are peaking on the left while the signal remains flat. So we can cut in here. The VDT that separates the two backgrounds, we have set plus jet on one side and TT bar on the other. We can cut here. And for the same sign, again, the signal peaks on the right. So we cut here and remove most of the background. Now, using these VDTs, we define the regions. So we put a cut on the VDT with the TSQ, define the signal region, and in the orthogonal region, with the other VDT, we define the control regions for TT bar and set plus jets. We do the same on the same sign. I also try to define control regions for TT plus X and TT bar separately, but this didn't perform well in the field, so I will stick just to a single control region here. Now, this strategy has been quite successful because in the signal region, we improved from you remember this small 0.02%, now we have 0.26. This is more than 1 order of magnitude of improvement on the signal to background ratio. For the same sign, the improvement maybe is not so impressive, but also very appreciated from 0.9 to 1.26. Observe also how our control regions are very pure on the process that they are targeting. Now that we have our analysis region, it's time to perform the fit. In the fit, what we use to compare our expectations to our observations. And this helps us to test the confirmation of the TSQ processes. The profile likelihood fit is a shape analysis, so it is based on the distributions of continuous variables. Basically, what we do is to minimize this likelihood function, and we solve this minimization to derive our parameters of interest. Our parameters of interest are the two signal strength, one for the opposite side, one for the same side, signal strength. And we can also use this fit to control some background processes. So in our case, we have as free-floating parameters of the fit the normalization of TT bar and set plus jet separately in the opposite sign. And in the same sign, we normalize the backgrounds with a pair of TT bar. These are TT bar, TTH, TTZ, and TTWB. And we normalize them simultaneously. In the fit, all the systematics are included as initial parameters, and those with a shape variation with less than 1% or normalization variation less than 0.5% are pruned from analysis. And well, we include all sorts of systematics, from the experimental uncertainties, being those of the luminosity pileup, the energy scale, the flavor tagging, and so on, and also the modeling uncertainties, which refer to the way that we simulate the processes. So for each process, we have like different modeling uncertainties. We also have modelings related to the choice of the generator that we use. We have a modeling bringing to the variation of the μR and μF scales, uncertainty on the cross section for all processes, except the ones that are fitted. And also we have systematic uncertainties on the method that we use to, well, systematic uncertainties on the template fit. And these are the regions that we decided to fit. So in the opposite side, for the signal region, we fit the VDT. In the control region, we fit the other VDT. And for set plus jets, we fit to HT to solve the fit for getting these parameters. Very similarly, in the same sign, we fit to the VDT and HT. Now, first, we perform the azimuth fit. In the azimuth fit, rather than comparing the observed data with our Monte Carlo, we compare our nominal Monte Carlo to itself, but this led us to assess the sensitivity of our search. And well, we saw that we don't have any significant constraint except those shown here, that we are constrained by the modeling of TT bar in both channels. Well, this is negligible. And also the jet energy scale and resolution, and we kind of expected these small constraints. We also look for correlations between our parameters, and in the opposite sign, we see that the modeling of TT bar is correlated with the signal strength, and in the same sign, our normalization factor for the backgrounds is heavily correlated with the signal strength. And well, this kind of makes sense, but we can discuss it later more. Now we can group our systematics according to the impact on the final uncertainty. And well, this large theoretical uncertainty comes basically from the modeling of TT bar. And it's also playing an important role, the energy scale and resolution in both channels. Now let's see the results of the Asimov fit. Here's where we can assess our expected sensitivity. In the opposite side channel, you see we are not super sensible, we have a plus minus 30 uncertainty on the signal strength. But most of this uncertainty comes from the systematics, which are TT bar mainly. On the other hand, the same side channel is much more sensitive. And most of its uncertainty is the statistical uncertainty. By the way, I didn't say it, but we know now the signal strength is just the ratio between the observed signal, the observed cross section and the one expected by the standard model. Now we can include our data into the fit. When we do this, some pools appear. Pools are the deviation of the nuisance parameters from the nominal values. And we have no significant pools except the ones I'm showing in this slide. Being the largest pool, the one in the TT bar modeling, and it's the largest in here and also in here. For the same sign, apart from the ones that appear on the opposite sign, we have also some pools related to the reconstruction of the taus and the method of deriving the fake factors. Again, the correlations are the same as the ones we saw in the Asimov case. And now these nuisance parameters can be ranked according on the total uncertainty. It is no surprise to see all the TT bar generation nuisance parameters on the top. And for the same sign is the norm factor, which ranks the highest. Also, the observed pools can be ranked according to their significance and the measurement of the signal strength. And of course, TT bar, but none of them very significantly. And here we have the tau energy scale in the most pool significance, although in this plot it didn't look like super constrained pool. Now, as we did in Asimov, we group our nuisance parameters by groups, and we can check our final uncertainties. The largest contribution, the theoretical uncertainties coming from the generation of TT bar. The energy scale and resolution, also relevant for both channels, is dominant in the same sign. And these are our results. We observe a negative signal strength in both cases, and while a negative signal strength is a physical result, it is compatible with the standard model predictions within the uncertainties. For the same sign, for the opposite sign, the systematic uncertainty is the largest one, and our normalization factors are hardly different from the standard model expectation and compatible with it when we take into account the uncertainties. We cannot say the same for the normalization factors in the same sign channel. Here we have our norm factor very far away from the standard model expectation and not compatible with the standard model within one standard deviation. Okay, there are several reasons for this to happen. And well, on one hand, the systematics from the template fit method, they are not properly derived, so they cannot account for the discrepancy between our data and Monte Carlo. Also, you see this very small scale factor. I think this small scale factor is because, normalization factor is due to the mismodeling between data Monte Carlo. And the reason to have this large mismodeling is because our scale factors are known to not be fully correct. So once this is fixed, this number will be closer to 1. And another reason could be that it has been observed a mild tension between the expectation and observation on TTWB processes on the analysis measuring this TTWB cross-section. And since TTWB is the largest background in this channel, this can also play a role. So here you see the results summarized. So you see how the same sign is much more sensitive. And we have just an uncertainty plus minus 5.5, all of it coming from the statistical uncertainty. For the opposite sign, the systematical uncertainty much larger than the statistical one. We also wanted to test the inverted Yukawa coupling hypothesis, and we did it in a very simple way. What we did is to use an alternative sample for the signal. So rather than using our normal signal, we used a sample that was generated using the inverted Yukawa coupling. But our observed data is still compatible with these changes. So we're not able to exclude this hypothesis. Finally, when our analyses are not sensitive to the measurement of the cross-section, we can always set an upper exclusion limit. And in our case, we can exclude signal strengths about 47 for the opposite sign channel and above 14 for the same sign. Well, I think I'm being quite fast. Nice. Now let's turn to our concluding slide, where I will summarize the key takeaways from our research, and I will outline also the contributions that I have done. So first, I have contributed to the performance of the Atlas detector by developing the web display for the monitoring of the inner detector. Then I performed a dedicated THQ search on 2 channels. For one of these channels, I successfully developed a method for assigning the origin of the light leptons. And for both channels, I successfully developed a method to define the regions of the analysis with very significant improvement on the signal to background ratio on our signal regions. Also, I work out algorithms to optimize the regions and the hyperparameters. With the fit, the signal significances that we have derived are fully compatible with the standard model. And from our channels, the most significant one was the one with the same sign leptons. This one was dominated by statistical uncertainty, while the other by the systematic one. We have set exclusion limits, but we were not able to exclude the CPD violation. Then for the future, the prospects for research are to include the TWH process as signal. Remember that in this thesis is presented as background, but on the ongoing Atlas search, I'm doing exactly the same, but using TWH as signal, so that we can study the entire TH production, which is what we should study to set to push the boundaries of what we know about the Yukawa coupling. Now, once I finish deriving the results for the TH study, my results will be combined with those of the other TH, and will be used to publish the first results of a TH dedicated search with the entire run 2 dataset. And maybe looking more into the future, I think this analysis will benefit from the increasement of luminosity in run 3, because with more available statistics, we can reduce some statistical uncertainties. I also hope that we improve the way we simulate our processes so that our discrepancies between data Monte Carlo are reduced. And I also hope to have improvements on the method to derive the estimation of the reducible backgrounds. All of these were major issues in in our analysis, and by solving them, I think we will strongly improve our results. Well, as I conclude, I think that this work does not only contribute to our understanding of the interaction of the Higgs boson and the top quark, but also encourages further investigations to push the boundaries of what we know about these two particles. And the only thing left to say is to you, thank you for being here and letting me join you in this scientific search. And to all of you that attended, thank you for your attention and thank you for being here. For real, thank you.
So we will now go through a few questions, and I suggest we do it topic by topic. So there's a committee, so we will start with like the first general introduction, which corresponds to the first chapter of your thesis.
Okay, can I start?
Yeah, indeed.
Right. Okay, well, I don't really have a question here, but just a positive remark, which actually when your presentation and also on your thesis, I realized that when you show the monitoring tool for the detector alignment, the data you are displaying there is data 23, so the latest data we are taking, which really speaks very well of the tool, because this tool was developed for run-through data. And still in use, still being in production. Okay, so I think that was a good success, or a good implementation of a tool which is lasting long and still being production. So in that sense, I'm quite glad to see that this concept. Of course, I can tell you that there are still a few things to develop. I already got some complaints that it needs to be moved further to Python 3. I'm not sure if we will be running on Python 2 as well, but that will be the task of some of the PhD students. So in that sense, I'm happy with this. I have some other questions.
Maybe, I don't know how much you really worked on the alignment, but I was wondering how much, what the precision is that you have reached at the end in the alignment. I mean, I understand the monitoring tool is just checking, but do you have a rough estimate on?
So my work on the alignment was not actually alignment analysis, but what I did was developing both the front end and back end of the alignment monitoring package. So I inherited a set of all packages, and what I did was to basically build the entire tool from the scratch and reducing the computational effort of running this machinery, as well as interconnecting the databases that were not included in the previous tool. As I also have refurnished the presentation of this tool, but it's not actual alignment analysis what I have done. So actually this tool could be used for alignment, but the technologies I used for it, I always make the same joke that I could have used it to develop the web page of a video club. It's just about interconnecting databases and efficiently calling the alignment scripts that produce the corrections and the calibrations.
So how did you fasten up with it, because it was written in some very old language and you found a faster way to do it?
I have this very joke slide that I did for one of the presentations that I gave during my QT. This is just a joke, okay? So this is what I found. I found a terrible mess of code. So very old databases that you had to be updating by hand constantly. Every time you wanted to change something, you would have to go to the code and hard code just for change the year. If you want to see the data from 2018, you have to go to the code and comment one number, put the other. And well, I took I would say terrible mess, but also kudos to the one who did it because it's not easy to build what was before and nicely organized. So what I did is first an enormous effort to understand how this web page worked. I then built on my head this chart. I did this chart on my brain to understand how the different scripts, because there were tons of scripts and they were all interconnected. So I did on my brain these for interconnections and translated into code. So the basic code was just Python 2 because it was what was available at the time. Actually, I wanted to do it with Python 3, but I think Python 3 was not supported by Athena yet. I may be mistaken on that, but I think it was not supported. So now it's Python 3. But I mean, I did this on. Look at this year. This is 2017. I don't know, but I have been here for a very long time. So in 2017, it was, even though Python 3 existed, Athena I think required Python 2, and that's why I developed it in Python 2. For the front end, I just learned to use HTML, CSS. I even did a small piece of code with Java. So now on my CV, I put that I know Java, which is a complete lie. For the optimization of the web page, I use a thing called Bootstrap, which allows, like for instance, if now you squeeze your screen, the display will be adapted to the size of your screen, so that now a shifter can just perform the sheet on their mobiles without need of a computer. So, is this replying to your question? No?
Yeah, no, more or less. I mean, it's. I think I'm always happy when I see this kind of development. I think it's understated how useful these things are and what's the great contribution the students have on this, especially when it makes things easier and.
Thank you.
Very nice, indeed. So maybe we move on. I think there's not more in this. So now going to, I think the next part would be more the analysis side, like all the reconstructions part.
Sure.
So you want to start?
Okay, I can start. So let me start by the early stages of the analysis with the fakes.
Wow.
Yeah. Okay, now we know the analysis is a big issue. But you mentioned it's very good that basically concentrated on the fakes of tau, which they are more complex objects than electrons and muons, but still electrons and muons they also have fakes.
They do also have fakes indeed. I have backup slides describing how the fakes from leptons are derived, but it happens as Carlos told me. You will put a lot of backup and then you forget where to put your backup and you will look on the main presentation. So
which is a good decision. So just tell me what you feel about.
I will just go to the main presentation and I knew that this was going to happen. So yes, we have lepton fakes and these are very small. But the way that we derive the scale factors from for the leptons is very similar to the way that we do it on hadronic taus. So first we derive the factors for the hadronic taus, because are the ones that have a more impactful role. But then we do the same for the leptons. We fit our Monte Carlo to the data to finish tuning this match. And in this case, we define the regions differently because since we have two leptons, we have regions according whether both leptons pass the tile identification requirements, whether the first pass it but the second doesn't, or the first does not but the first pass the tile requirements, or finally the region in which both leptons fail to pass the identification requirements. So for each of these regions, the fit is performed separately. And let's give it a chance to look for the slide. So maybe so many backup slides. Maybe this was a mistake.
You don't need to go to the slide. That's
To the slide in which I described so these are the regions, no? So we have two leptons. These are the regions we define, and we use the lepton templates to fit in these regions. So this is how our distribution looks, and this is how we fit. So we have the two leptons passing the tide, one, the other, or two failing, and we see whether this category is the sim, jet is whether the reconstructed lepton matches to a real lepton, like to a truth lepton or not, and this is how we perform the fit. Of course, we also make this separation we split it in several control regions and by PTBs and so on.
Maybe since we are on the on this level, so for the taus, I mean, you also did the tau reconstruction, and you have scale factors for the tau efficiency as a function of PT, right?
Yes, as a function of PT, in terms of PT, progness, and multiplicity of digits.
So how did you determine them? How did you find them? I mean, you need to have a reference, right? Data. I mean, Monte Carlo is easy, as you said. Yes. You know what is the truth, so you can just see whether you reconstruct it. But in data, how do you know what the right reference is?
In data, we don't know the right reference. We cannot know it in data. So the purpose is just to know it. We only need to know this. Imagine that we knew data, it would be just amazing. No? We need these tools. So in data, we don't know, but we know in the Monte Carlo. So we just we define the regions by looking at the Monte Carlo, and then in these regions, the Monte Carlos, in which the truth identity of the particle is known, a fit is performed to the data in these regions. But to the data itself, it's not possible to know the true label, of course.
Anything else in this reconstruction? But you don't happen to have a PT of the taus. It's so important for you. The efficiency scale factors, you don't have it in your backup, no?
No, actually,
but it's not so bad.
I didn't work much directly on the derivation. I mean, I know the process. I studied it. I benefit from these tau scale factors, but they are not the main part of my work, of course.
Okay. Anything else on this reconstruction? Okay. So maybe then we move on to the analysis.
Okay. Sure.
So I had a question to this pre-selection that you applied.
Okay. Do you want me to go to the slide?
Maybe, yes. So for the same sign analysis, I think what I actually wrote it down. Page 35. So yeah, something like that. 34. Perfect. Yes. So this same sign analysis is super fascinating because you get rid of so much background and it's really beautiful. So I really like it. But you have the problem that you have a Z background, right?
Oh, what?
The Z plus Z background.
Yeah.
So I was wondering, why are you not just cutting on the Z mass peak and removing this? Or did I not see it?
Well, there is a reason. So we could apply this type of cuts.
As a veto, of course, right? As we do in other analyses.
Yeah, so you say, I veto this, and so it does not come into the preselection. But instead of doing this, I decided to let the DBDT use this variable and further decide how large the window should be, or because maybe these events maybe maybe help us to further adjust the normalization factor of the Z jets, but mainly the main reason is because I thought that the PDT will be wiser in terms of deciding which cuts to apply on the Z mass. And in fact, this is what happened in the PDT of TT bar. You see that the highest rank variable is this peak of the Z mass.
Maybe since we had this slide, another question. Why do you include events with 2 B jets and not just one? Because with the 2 B jets, you buy the TT bar background, right? And if you have a single top, you only have 1 B jet, right?
We consider removing events with 2 jets, but when we look at the distribution, we still have some data in this region, some signal data. And since one of our problems is that we are so scarce of signal, I mean, you see here how, changing to the next slide, no, I am not. Well, I lose control of the presentation, but it's fine. No, not anymore. So we see we have such a small amount of data, this 193 on the opposite side versus 10,000. I mean, we have nothing. So we wanted to keep as much signal as possible. And since in the 2 jet region we still had some data, and now I'm thinking maybe it should be nice to have the BJet distributions, but I didn't do it. But in the region with 2 jets, we still had signal events, and we couldn't afford to ignore them.
Okay.
Yeah, well, the selection of the when you were trying to make the matching between the different.
Yes. I love this slide.
I think what I have in here was page 13, no, 41, page 41.
Oh, I'm 41 now.
Yeah, okay, on this statistics plot, okay, what you show us, okay, you are trying here DDT just to see which leptons have to be, which is a partner of which one.
Exactly.
But then, okay, it's quite clear that the statistics here is quite scared as well.
Yes, limited.
Sparse. So what is why there is so few events? Because there was not enough Monte Carlo, because the selection really cuts away all the.
So these are the events that we use, and we try to be as inclusive as possible when cutting what went into the training. So the first filter that we have is the selection filter. So then we demand only signal. This VT, I didn't say it, but it's only trained on signal events. So we are having less and less events. Now, I train it only on the same sign channel. For the principle, I don't see now. I could have also used the opposite sign for the train, but it's trained only for the same sign. So now we're getting like less and less data. Then we require that the hadronical indicating tau comes from the Higgs boson, because if it had came from the top, then the definitions of lepton from Higgs and lepton from top would have not made any sense. So at each step we use some events, and finally we only are taking into account the TP and WBK modes for the labeling. In our analysis, we also have set, but in the labeling, set is not included because it was a very small fraction of the events, but there were way too many configurations to have the lepton final state in the same with the set. So all of this causes to have smaller and smaller events, as amount of events. So what we did is to select a beta cone that include as much as possible events. So you see that the vast majority of our events is in a very limited scale. So this is basically everything is included on our training. But in the end, the statistics will be very limited.
Will the opposite sign events be included here in the training?
So I
The
have
kinematics and all that is the same.
So there are like several remarks. So the opposite sign channel has not been included in this training because since I wanted to apply it only on same sign, I trained it only on same sign. Nevertheless, in principle, there is nothing that would change from apart from the electrical charge, but the kinematics of the same sign and the opposite sign more or less should be the same. Therefore, we could benefit from the opposite sign channel also in the training on visibility, and we would double our statistics. Nevertheless, the reduced statistics performs very good. Now, about the systematics, we do not derive any systematic from the training. TMBA has a tool that provides an uncertainty on the score. So it's like, did it get a score? Did it get a score error? But this tool has never worked, not for me, but for the TMBA community. This is still under development. And well, I hope that they finish developing this tool because it would be very interesting to derive an uncertainty from whatever uses ability, in my case, uncertainty from the lepton assignment method.
I have a curiosity about the lepton assignment. I was wondering if you have an idea, this is just a curiosity, on what's the gain of having this two-stage approach. As I understanding you define the lepton assignment, you say, okay, this is most likely my lepton from the Higgs or my lepton from the top, and then I'm guessing you build some variables to
Exactly.
that then you feed into the BDT for the written definition.
Exactly.
What happens if you just do one single BDT training, then you just do everything on one stage rather than two stages?
So I think you're asking then about why we use lepton from Higgs and lepton from top categories rather from leading lepton and subleading. And I don't have backup on this, but I remember I put a very nice plot describing this. And here you see our distributions using, I don't find this. Maybe this is on an old draft of the thesis because I don't see them. But you could see in this plot.
I remember it wasn't a pre-version. I remember this.
Yes.
It was really nice.
I don't know why. I think the thesis was too large. Anything was too expensive. Some plots have to go away. But she remembers, for me, you know. So if you look at the distribution separating signal for background, the distributions using variables with leading and subleading leptons, and the same distributions, but rather than talking about leading and subleading leptons, we would talk about lepton from Higgs and lepton from top. And when we use this nomenclature and this definition of leptons, the separation from signal and background was larger. These variables provide their discrimination. And I observed this on the opposite side channel, where it was very easy to have this distinction. And since in the opposite side channel, they provide such a better performance in terms of discriminating signal and background, this motivated me to develop the method to define the label now in the same sign. Sorry that I removed that from the thesis. Now I see it like super important.
Okay. Maybe more on this, or we'll move on to more high level. Let's see. Yeah, I had a question. If you go further on, there was you also mentioned during your talk that you combined the backgrounds of TT bar and TT plus X, and you said the fit didn't quite work. So I remember actually from your thesis again that somehow there's a slight difference between TT plus X and TT bar in HT, for example, right? Or, so if there was enough power in the fit, it would, from shapes, there should be strength to constrain it, right? But you say this did not work?
Yes, exactly. So I always put the previous slide because we don't see the same screens.
Exactly. Here you see the shape, right? Yes.
Exactly. So The idea was to separate somehow the TT processes in here from this region, which is super pure in TT plus X processes. And well, I don't have the numbers now, but we could achieve like relatively good purity in our control regions, but it was not enough. We maybe didn't have enough statistics on our field. So actually the strategy that we follow to decide whether to use this approach or this approach was by testing both. We performed the azimuth fit and the control region background only fits with both approaches, using the single control region and the two control region strategies. And the single control region was much more stable in the fit. The fit performed simply better. I think it's because the amount of the statistics, the fit, so some regions in the two region scenario, probably this one, had very small statistics, and this is where the fit exploded.
I think you would definitely need 1.3 for this analysis to show all the hard work that you did to flourish in with more statistics, right?
Yeah, definitely.
So,
Can I go one step back?
You can go wherever you want.
So when you were showing the training of the utilities with this scaffolding and so on.
Here.
So let me see if I understood. So you divide the sample, the Carro sample in 5 folds. The question is, are they independent each other, or are each test, or are they kind of bootstrapping where they have common events?
You mean,
You didn't really get the.
are you asking about how I divide events, like the methodology to divide events? Well, these events, the division is done with an split expression that takes the random number. And this is fine because the random number is just a tag that we put on our events, but it has no physical meaning. So by dividing by the even number, we are not biasing in any way our way of splitting. For instance, if we have split it using our PTs, then each sub data set would have a very different physical characteristics. But our way of splitting using the even number, it's a random splitting. And therefore, every subset, either here or in the other PTs, is representative of our entire data set. So this way we don't have biases. Of course, for the lepton origin, since we have so little data, any fluctuation would be more visible, but basically the division of these splits is completely unbiased.
Okay, so here what you're trying to do is to make sure that you are not biasing the.
Exactly.
So it's not a question of just taking an average of the outputs or whatever. So you just want to see that whatever the training you do, your training is giving the same results.
Yes.
Within errors.
Exactly. Well, yes, for the other DDTs, the one of region definition, and these are on the thesis, you could see how our distributions evaluated on the test samples, this is important. So our distributions evaluated on the test samples have exactly the same shape. And this is, remember this histogram with having all the folds in different colors. Now you will see our AOC curves, and they will have exactly the same shape. These lines will not separate, not even a bit. So yes, our performance of the models was exactly the same. And here, due to the lack of statistics, we have some small discrepancies on the behavior, but this is probably within the uncertainty of the method, because remember that for this PDT we didn't have that much data. This was so this is kind of inevitable to have a small effect on the faults that we use for training because there is so little data. But yes, in principle, this, if you could see the distributions for each fold, these BDT scores for each fold, they would look basically the same, and most of the discrepancies would be just like in these regions here that are very irrelevant.
How did you combine them? You have 5 at the end, right? You have now 5 different BDTs with
Yes.
different set of cuts. So how did you combine them at the end?
Well, the combination is to each event, I apply the BDT that was used when this event was part of the test sample. And this is just one BDT. Each event was tested only once. So this is the way it is applied. This is the
But
combination.
when you have real data, you didn't do anything of this. I mean,
No, on real data, this is random.
so you take just one of them.
No. Not, of course, exactly. For each data event, I take only one of these BDTs selected at random.
I see.
But this is precisely what we want to do. We want it to be random. And in principle, since all the 5 BDTs behave the same way, it should not matter which one we use. Actually, I guess that if we use just one, we would be biasing ourselves more than if we did it randomly. And the way we select this random way is also according to the even number. And this not only applies to the signal data, this also applies to the backgrounds. And we derive the lepton from Higgs and lepton from top labels for backgrounds, even though this label has no physical sense for the backgrounds. But it is applied as well for the backgrounds, and none of the backgrounds were included on the training. But always, one BDT is applied to each event. For the signal, we use this criteria, but for all backgrounds and for the data, is one of these 5 at random.
Other questions? No. Maybe we go to the results. So now you got a negative mu. So,
Yeah.
So what does it tell us?
Well, what I read from the negative mu.
I mean, first of all, are there other options? I mean, you could have avoided it, right? I mean, you could force your model to be positive, right?
What the negative mu tell us is basically that our modeling is very bad. I mean, normally we would expect a signal strength or a normalization factor to be something between 0 and whatever you want. So if we have an excess of data, of Monte Carlo over data, then we need to scale down the Monte Carlo. But having a negative mu would be having a negative number of events, and you cannot have a negative number of events, of course. This makes absolutely no sense, and this comes from terrible modeling. It is what it is. We have terrible modeling, and this gives us this negative signal strength.
But have you considered to force? I mean, you can force a fit to only allow values up to 0.
No, I have not considered this option, but then I guess it would
maybe go to KTT bar. Right?
Exactly. Also,
where it should go.
All this, yeah. Now that you mention it, they're much clever now, because our mismodeled is mostly from the misidentified backgrounds, and this should have eaten all this reduction. Yeah, you are completely right. And
well, it's a choice. I mean, what you did is perfectly fine.
And
CMS also has this for TTH that published the negative.
We did as well.
Yeah. So it's perfectly fine. I just say it's just to try it out and see what happens.
It would be
nice exercise.
A great test, of course, to see what would happen. Another reason to do this is to align with the rest of the TH analysis, because they are also using this. But yeah, certainly we would have the null factors would have eaten all of this.
Yeah, exactly. So by the way, I mean, it's already NLOTT bar, so we would expect it to be quite precise, right? So what is driving this? I mean, for the lower one, I understand it's CTW, but for the upper one, actually, you also get quite a good precision. So what is driving this uncertainty for TT bar?
I think it's because we are not using the latest recommendations. So I think the latest recommendation is to use PTR1. And well, on the TH analysis, I'm using tuples with the correct TT bar modeling samples, but for the tuples I used on the THQ search, I had the old TT bar. So probably that is what gives rise to all this mismodeling.
Okay.
But in this case, okay, we are saying that the modeling is not as good as it should. But how we can improve it? Is really a modeling of the tau scale factor, or is it really a modeling of the backgrounds of the next to next or next to next to next leading over?
So from the background, sorry, I interrupted you.
That's my question. It's a generic question. What can be done?
Well, I think everything could be improved, but from the backgrounds, from the modeling of the backgrounds, what we get from here, of course, can be like some mismodeling, but mostly from the choice of the way we simulate TT bar, we get a large uncertainty on its generation. But the source of mismodeling, the large source is the way that we apply the fake factors that account for the rates of the reducible backgrounds. We know that in these tuples there was a bug including the scale factors. Actually, in the coordinate tuples there is also a bug when including the fake factors. This is where the large modeling appears. So this would be the first thing I would fix on the analysis. And well, this has been now studied, and I really hope that in the next weeks the solution is ready.
Okay, just a final question on your future prospects. Okay, you say you want to combine this with other channels. Just a generic question again. Do you know if the other channels have what is the sensitivity of the other channels?
Well, it is a bit better than mine. So I know the results just for the multi-leptonic channels, and for both two leptons same sign and 3 leptons, well, everything has better sensitivity than opposite sign. Opposite sign is the worst of the channels from the multi-lepton ones. But I have here, this is mine. No, this is not mine. Perfect. And then this is the channel with 2 atomically different towers. And for the team that is searching this channel, they found that it is more sensitive even than the same sign. So this will already, this is one of the channels that has better sensitivity than the ones I have used. Now we have the channels with 2 leptons and 3 leptons. Okay, well, 3 leptons does not provide better sensitivity than my same sign. 2 leptons same sign has a similar sensitivity to my channel. Yes, this is also worse than my channel. So yeah, I would say that my same sign channel is the second most sensitive channel out of all the multi-leptonic channels. And my opposite sign is absolutely the worst.
But the same sign would be powerful. I mean, just like statistics, right? So that's a
Exactly.
future. So it's
exactly, it's clear.
Yeah, it's a bright future.
Exactly. I mean, by just increasing the statistics, the sensitivity of this channel would be just super greater, because from our this 5.5 of uncertainty, 5 is statistical. So more luminosity. This, I think this channel is super promising.
Is there a calculation? Is it expected for 1.3? It should be whether there's a discovery chance now.
Well, since I don't know, since the collision energy improved a bit, the cross sections of the processes also changed. Probably not much because we didn't have improved the energy a lot, but the cross sections would change for not just for our signal but also for the background processes. So maybe this can affect the relative contribution of the signal to versus to the background. So I wouldn't be able to make a guess.
Yeah, maybe for yt minus 1.
Sorry?
Maybe run 3 to exclude completely
Well,
yt minus 1.
Well, certainly we are very on the verge of excluding it. So yeah, if we reduce this number, maybe we can exclude it. Although I may note that this is a yt minus 1 just on the signal sample. Maybe for properly excluding it, I would have to change the Yukawa coupling not only for the signal but for all the processes that are sensitive to yt, which I think is just th if we are talking about the sign. But if we want to test different yt's, also th.
Okay, so thank you.
Thank you.
It was a very good discussion. Yeah, so was just reminding. So anyone with a PhD is allowed to ask further questions to Pablo. No questions? Well, the presentation was super clear. And we also already had lots of discussion. So thank you again.
Thank you. Thank you. Thank you all.
We will have now a closed section, so I have to ask the audience. We are staying, so the audience needs to leave.
Okay.
Yeah, and Johannes and Susanna will stay,
La portada.
So, Pablo, now you see
La portada.
la portada, of course, the screen.
Okay, so maybe this. So
Bueno, I would like
you want to have
a
the
nice
thesis.
background image
Nice background image.
for
Yes.
the people in Zoom. I'm sure this is the fastest way.
Let's see. Indeed, yeah, this is much nicer. I agree. So yeah, so the committee has decided, thanks to your great work and a very nice presentation, to give you the highest grade. So congratulations.
Thank you. Thank you very much.
All the best for you.
Thank you.
Thank you, supervisor. Okay. So now that you got, but we also thank the supervisors for the excellent work for getting Pablo to the stage to become a full PhD physicist.
Ara deixeu-me dir que Pablo sempre m'ha sorprès. Primera vegada. Sempre m'ha sorprès que havia continuat sorprenent-me, sempre gratament. I el que puc dir és que, bueno, ojalà en este món hi hagueren més Pablos, molta més
Ai,
seguida.
para.
Seríem molt millors. Moltes gràcies.
Sí, ¿no?
Well, congratulations.
Thank you very much. Mira,
Voy.
estoy teniendo un bajón de azúcar.
Congratulations.
Everything is moving now.
So congratulations.
Thank you. Thank you very much. But I knew that I will have to talk. I knew that I didn't prepare any work. Well, first and foremost, thank you, Carlos and Susana, for your help. None of this would have happened without you, and you are the first people to thank for this thesis. From the bottom of my heart, thank you very much for your help. To the committee, thank you for traveling here. To Salva, thank you always for your infinite kindness. To my PhD peers, thank you for joining me in this amazing adventure, and to my family. I get emotional very easy, but I guess this is fine. So to my family and friends that have gone, some like David that has come from CERN just to attend to this defense, or Hector that has traveled from Madrid just for a single day to see this. I think it's a very lucky person in terms of having the best friendships and a family. So you are here, and I want to thank you for your infinite support. So this thesis is yours. Thank you. Now we go